All right, so the exam was due yesterday at midnight, so hopefully everybody here and watching this did that already. What we have for assignments this week is the Chapter 2 homework quiz and the discussion for Chapter 2. So the discussion, it's worth 10% of your grade, and a lot of people are forgetting it, so try not to forget any more of them. If you've only missed a few, you just missed a few of the points, because we're going to have discussions every week. They're always due on Sundays. When it comes to Sunday, think, hey, have I posted anything? It can be questions, it can be practice problems, it can be videos you found that's helpful on the material, really anything, just a combination of things. You need 2 posts to get full credit. Okay. And even if you don't have a question, just post a question that you've made up for someone else to answer. So it can be anything. I'm just looking for interactions between students. All right, so both of these are available for you now in the week 4 folder. The homework quiz, I believe, is 15 questions. And it's going to be on stuff from the PowerPoint, which are some definitions and things, and then mainly actual word problems, which is what we're going to focus on in class. So what I'm going to start with is looking at velocity problems. So we have 2 different types of velocity problems we're going to approach. We have a 0 initial velocity. So this is where the object is at rest. So it's initially not moving, it's stopped, it's parked, it's still. Okay, so I'm just going to put at rest above that. Then we have the non-zero initial velocity problems, and those ones are going to be where the object's in motion at the very beginning of the problem. So a car that's already going, 70 miles per hour, something like that, so already in motion. Hence the non-zero. And you'll see the difference. So when we're looking at these equations, they're very similar to each other, and I've lined them up so that they kind of match. And the only difference between them is that the non-zero initial velocity problems have this v sub I in it. And that's because its initial velocity is not 0. So you will have a number that you can insert in there. So that's what that I means, is initial velocity. So what I have down here, and you'll also see this on the PowerPoints, are just the definitions of the variables themselves. Because what we're going to do, how we're going to approach all of these problems, is we're going to take all the numbers presented in the problem, and we're going to write down what variable they represent, what letter they represent. That way, since there's so many equations to choose from, we can go, okay, I have these 3 variables. Which equation is going to work for me? All right, so it's important to know what these variables stand for so that you can label your knowns and unknowns from your word problem correctly. So D for distance. Another thing that's important are the units. So in Chapter 1, we did tons of conversions. We were all about units, and this is why. We're going to be using units. We're going to be doing conversions in Chapter 2, Chapter 3, Chapter 4, the rest of the semester. Okay? Why? Because when we use these equations, we need to be in metric. We need those SI system units that we talked about in Chapter 1. So distance needs to be in meters. Velocity, which is like a speed, okay, so think miles per hour, except for the difference between speed and velocity is velocity has a direction as well as a magnitude, so it's a vector quantity. And if you have no idea what I'm talking about, watch the PowerPoints, and I give the definitions on scalar and vectors, as well as several examples. So velocity, we don't want in miles per hour. We're going to want it in meters per second. And I have posted an equation sheet, and you'll have to excuse me because I labeled the top of the equation sheet wrong. Notice it says Chapter 4, Equations and Conversions. So you can find this in your Week 4 folder. So this used to be our Chapter 4 last year, but we've changed the orders of the chapter now. So these are the correct equations. It's just we're now calling it Chapter 2 since it's the second chapter we're looking at. So I will try to go in and correct that. But if you've already printed it off, it's labeled incorrectly. These are the right equations for this chapter. So you'll notice with that equation sheet, the reason I grabbed it in the first place, I give you conversions at the top. And the very first conversion is going from miles per hour to meters per second. You're going to be using that conversion factor so much, you're probably going to memorize it. Okay? Because here in the US, when you're driving a car, you have miles per hour on your speedometer. Well, in order to use these equations, we need our velocity in meters per second, so we're going to have to convert that. If you see this V sub av, that's just average velocity. So just look closely at the words in the problem to figure out if they're looking for velocity, average velocity, initial velocity, what are they asking for? We have two more variables left, acceleration. The units on that are going to be meters per second squared. I don't think I ever ask you to convert that. So you'll always be given acceleration in meters per second squared. And then last but not least, time needs to be in seconds. If it's not, you need to convert it. That's why I have the conversions, which you probably already know these. 1 hour is equal to 60 minutes, 1 minute equal to 60 seconds. So you can always use those to convert either minutes or hours into seconds if you need to. So let's look at how we're going to apply this. Okay, because this is the part I can't cover on a PowerPoint, right? Step-by-step problems. So the first problem we're going to look at is, say you get into a parked car and you start accelerating. You get up to 35 miles per hour. It takes you 4.2 seconds to get to that velocity. We want to calculate the rate of acceleration and the distance covered. So the first step is to label your knowns and unknowns. I'm going to do this before I convert, just because that will help me figure out what I need to convert. So when I say knowns and unknowns, that means I'm going to be taking all the numbers presented to me in this word problem, and I'm going to label them with one of these variables. Once I have them labeled, I'll be able to look at units and see if I need to convert them or not. Okay, so those would be my knowns. The unknowns are going to be, what is the question asking for? What do I need to solve for? Okay, so I'm going to put both, just write them in a column so I know what I have and what I need to get. So the first piece of information when I'm going through here that I encounter is this 35 miles per hour. So looking at the variables, I need to figure out what that is. Okay, well in this case, that's not a distance. It is, however, a velocity. Okay, so 35 miles per hour. Whenever you see miles per hour, meters per second, it's a velocity of some sort. Now, it could be initial velocity, it could be average velocity. I'm going to use the words around it to figure out what type of velocity it is. Okay. Next piece of information, 4.2 seconds. So what variable is that? In this case, seconds, time. It's how long it took, right? So these are my two knowns. Those are the only pieces of information given to me in the word problem. However, it next says calculate the rate of acceleration. So acceleration, this A, that's one of my unknowns. So I'm going to write the variable A with a question mark. The reason I'm doing this is because I'm taking these variables and I'm going to compare them to the equations I have to help me figure out which one's going to be useful to me. So A is one of my unknowns, but then it says and distance. So distance is going to be my other unknown. Now that I have my knowns and unknowns, before I pick an equation, I'm going to do my second step, which is convert if necessary. So you're looking at just the knowns, the pieces of information given to you. Do I need to convert? Well, time is in seconds. Looking at time, I want it in seconds. So I don't need to convert time. However, velocity, we want it in meters per second. It's not. It's in miles per hour. So that's going to be my first, the first and only thing I'm going to convert. So I'm going to take velocity, 35 miles per hour, and I'm going to convert it to meters per second. This is just like the conversion factors we did before. Okay, think English to metric conversion factors, where you need to find a conversion factor, and it's the very first one on your Chapter 2 equation sheets. So my conversion factor is going to be 1 mile per hour is equal to 0.447 meters per second. Okay. So once you have your conversion factor, you can do that RoboTrack method. exponential analysis. Okay, and what you're going to start with is the number you're trying to convert. So I'm trying to convert 35 miles per hour. It's going to go in this upper left-hand corner. And I'm going to take my conversion factor and plug it in here. And I need to figure out which way to put it. So do I want the 1 mile per hour portion on the top or the bottom? That's what I'm trying to figure out. And remember, we're trying to cancel out miles per hour. So we're going to take the 1 mph, the 1 mile per hour, and put that on the bottom so they're on opposite sides of this horizontal line, canceling each other out. And that's going to put my 0.447 meters per second on the top. So 35 miles per hour in meters per second is 15.645. Notice, I'm not worried about sig figs right now. I'm going to worry about sig figs. I still am. We learned it for a reason. But I'm not going to worry about it until I get to my final answers. This is not a final answer. This is a conversion to help me get a final answer. So I'm going to keep all the digits presented so that I get a more accurate answer. So this is the velocity I want to use once I figure out what equation to use. All right. So I'm going to erase the conversion section so that I can do my third step, which is pick an equation. I'm going to run out of room here on the board. So now that everything's in the correct units, I can pick an equation. And I'm going to solve for, I have two different equations I'm going to need. So if you have two variables, you're going to need two different equations. So just focus on one and then worry about the next one. So let's do acceleration first. So I'm going to pick an equation to solve for acceleration. Okay, well to do that, what's going to help me now is reading the word problem and figuring out what type it is. Okay, was the object initially at rest or was the object initially in motion? Well, you got in a parked car. Are parked cars initially moving? No. So we're looking at this section. So we just narrowed it down to one of these equations. Okay? So what we want to do is look at the variables we have. So we're solving for acceleration. So we want an equation that has A, T, and B in it. So going down here, we have a D. So it can't be that one because we don't know what D is. So that's not going to help us. The average, no, it said nothing about average velocity. Keep going. This one has a V, A, and a T in it. But notice, so does this one. So I'm going to pick the one where A is equal to, because that way I don't have to rearrange the equation. You can pick this one, B is equal to AT. You're just going to have to rearrange the equation to solve. So by picking the A is equal to V over T, it's already rearranged for us. So it's just going to save us some trouble. Now, just plug it in. So to solve for acceleration, we're going to take the velocity and make sure you're using the meter per second velocity. And we're going to divide it by the time, 4.2. Now, since this second is actually in the denominator, we're taking seconds and multiplying it by seconds. So what I mean by that is that's why the units are meters per second squared for acceleration. They're not canceling each other out, we're actually multiplying seconds by seconds. All right, so when we divide that out, now is when we're going to want to worry about significant figures because this is one of the answers for the question. So I get 3.725. If you get something different, please let me know. If you're calculating these two, because I press wrong buttons all the time. So now we're looking at sig figs. So to figure out the sig figs, we're looking at the significant figures given to us in the problem. Not the conversion factors, just the problem. So velocity had a total of 2 sig figs. The time given to us in the problem also had 2. So that means we want our answer to have just 2. So going over here, the 3 and the 7, look to the number next to it, it's going to stay a 7. So the answer to the correct sig figs is just 3.7 meters per second squared. So the car is accelerating at 3.7 meters per second squared. Try I was going to say density. That's not density, that's distance. Should we try distance next? So it's the same problem, just now we're going to solve for distance. So I'm going to put my acceleration, I'm going to fill it in because it's not an unknown anymore, it's now a known. So I'm going to pick another equation for my second variable because this is a 2-part problem. And on the exam and the quiz, they'll all be 1-part problems, but I just wanted to show several different types of equations. That's why I'm doing 2 unknowns in one. So we need to solve for distance, meaning we need to pick an equation to solve for it. So we can have an equation that needs a D, A, T, and a B in it, or a combination of those. It doesn't have to be all of them. First one has distance, but we don't have average velocity, so we keep going. The only other one that has distance is this bottom one. So let's write that equation down. Distance is equal to 1/2 AT squared. So this A being acceleration, almost like an E there a little bit. So for this, to solve for this one, we don't need velocity. We just need time and acceleration. So we just plug those into the equation and solve. So really just finding the equation is the hard part, because once you have it, unless you need to rearrange the equation, it's really just plugging in what you have into your calculator. And time was 4.2, and I'm going to make sure to square that. And this time, I should get a distance in meters. 32.6. Okay, but we want to keep with sig figs, and remember we said 2, so we only want 2 sig figs in our answer. And this time, we have to round up. This will be 33 meters. So what that means is to go from 0 to 35 miles per hour, that car covered a distance of 33 meters in that 4.2 seconds. All right, let's try another one. So, next one we're going to look at is a stomp rocket. So if you've watched the PowerPoint, probably heard me talk about a stomp rocket. For those of you who don't know what a stomp rocket is, it's a kid's toy. You literally stomp on it. It's a little pump that has a foam rocket on the other end, so when you stomp on it, the air shoots the rocket into the air. So stomp rocket says that it can go how far did it say it can fly? I even looked up this. This is the actual value that it says. It says it can fly 200 feet in the air. Now, I have 2 kids. We have one of these at home, and I've never seen it go that high. But I'm sure they got it to go that high once, and then they can do that, right? So we're going to calculate the acceleration. All right. Markers. Stomp rocket says it can go 200 feet in 3.2 seconds, so it can shoot that high up. All right, well, let's calculate if it could do that, what's its acceleration? What's its rate of acceleration? All right, so start off just like normal. Knowns and unknowns. See what we have to work with. And I know that writing this all down sometimes can get a little tedious, but we're only going to be adding on to these equations. Okay, so keeping an organized, systematic way of doing this is really going to help you going through all these chapters. So the first piece of information that I see, it can go 200 feet. So let's assign a variable to that. 200 feet would be distance, okay? Now, it's not in the units we want, I can already see that, so I'm going to have to convert, but it is a distance. It's a height, distance, they're all the same thing, so I'm going to represent that with the letter D. Second piece of information, time. Seconds is always a time, and that's already in the units we want. If we're not sure, we can always just check. Time needs to be in seconds. Good there. Now, what are the unknowns? So this time we only have one. It wants us to calculate the acceleration. Acceleration represented by the variable a. I'm going to put a question mark because that's what we're solving for. So, second step is, do we need to convert? Convert if necessary. And we do. We just said when we looked at distance, we're like, okay, that is distance, but we need it in meters to use any of these equations. So we're going to convert 200 feet to meters. So for that, feet and meters, this is English to metric. So we need a conversion factor. So you might be using that conversion factor sheet from chapter 1 once in a while, but I tried to have the most common ones on this chapter 2 equation sheet. And you can see that 1 foot is 0.3048 meters. So you set up dimensional analysis. The number you're trying to convert is the 200 feet. So you start with that. With the conversion factor, the 1 foot will be on the bottom to cancel opposite sides of that horizontal line. And then the 0.3048 meters is going to be on top. So you're multiplying over 200 times point. And remember, since this is just like an intermediate step, we're not going to worry about significant figures. Actually, turns out it has exactly as many as you need, but we're going to take this number and replace it where distance is. Because this meters is the version that we want to use in these equations. All right, so knowns and unknowns, done. Convert if necessary, done. Step 3, find an equation and solve. In this case, for acceleration. So this one's going to be a little bit harder. I'll see why in a second. When you're looking for an equation, you need to figure out what type. So the stomp rocket, you need to know what one is to figure out the type. And I said it's basically a pump with a foam rocket on one end. So is that foam rocket initially at rest or is it initially in motion? It's at rest. It's sitting there on the peg. Okay? So we are using our zero initial velocity equations. Now when we use them, we're going to try to find one that has these 3 variables in it. That's why we wrote the list in the first place. It's going to help us when we come over here to choose. Now notice the one I used last time for acceleration in the last problem has a v and a t. We don't have a velocity. We can't pick this equation this time because we have 2 unknowns and we can't have that. So looking at the other equations, that one won't work. So just kind of systematically go through and see if any of them are working. And you'll notice that this bottom one, this is the only one that can work in this case. Because distance, yes, we have it. Acceleration, no, that's what we're solving for, but we do know what time is. So we know 2 of the 3 variables, so we can rearrange this equation and solve. Okay, so sometimes on the harder ones, you'll have to rearrange. So by rearrange, what I mean is we want to get a by itself. So we want a all by its lonesome on one side of the equation and all the other variables and numbers on the other side of the equation. So how do we do that? Well, in this case, what we're doing is we're taking 1/2 and we're multiplying that by a and then multiplying that by t squared. So to get rid of the 1/2 and to get rid of the t squared, we need to do the opposite operation. So since we're multiplying a by t squared, to get rid of t squared, what we're going to do is, what's the opposite of multiplication? Division. So if we divide by t squared, notice we have t squared on opposite sides of that horizontal line. That means they're going to cancel. So we're getting rid of the t squared on this side. But the rule is, whatever you do to one side of the equal sign of the equation, you have to do to the other. So since I divided by t squared over here, that means I also have to divide by t squared on the other side of the equal sign. So now what I have is d divided by t squared is equal to 1/2 a. But notice I'm not done, because I want a by itself. I gotta get rid of that 1/2. Right, so to do that, I'm taking 1/2 and multiplying it by a. So I want to do the opposite operation. Opposite of multiplication is division, so I'm going to divide by 1/2. Which is really like multiplying by 2. So your choice, you can do it either way, you'll get the same answer. So 1/2 over 1/2 is just equal to 1, they cancel. But I have to do the same thing on this side of the equation. So you can have it written out this way, or if you actually take this and flip it, it's the same thing. So 2d over t squared is equal to a. So this is going to be my rearranged equation, solving for a, and now I can plug in my two known values where those variables are and solve. Out here. 2 times d, we said our distance was 60.96 divided by t squared on the bottom, so that's 3.2, and we're squaring it. I got 11.9. Accelerates a lot faster than the car from the previous problem. Now, how many sig figs do I want though? So let's go back to sig figs. My distance, initial distance, had 4. So the decimal point there is saying the zeros matter, so total of 4. For time, just the 2. Pick the smaller always, so that means my answer should just have 2. Boom, boom. In this case, the number next to it means we round up. So it's going to be 12. And since the acceleration, when you're looking at units, it's meters per second squared. So a lot faster acceleration than the vehicle. What was the vehicle in the last one? 3.7 or something around thereabouts? So the hardest part of this problem is rearranging the equation. And that'll get easier with practice. All right, keep on going. Another one. So in class, whenever you're watching these videos or coming to class, I'm focusing on just solving the problems, but there's also going to be definitions, so make sure you are watching those PowerPoint videos. I mean, you do have a book available to you, an online book, but I pick out just pieces of information from that book that you need to know. So watching just the PowerPoints will be enough. You won't need to read the book as well, unless you want to, which is completely your choice. But you still have to know definitions that I'm not covering during these in-class videos. So, moped, moving, 22 miles per hour. Decelerate. A lot of new stuff in this one. Just going to find a better marker when I keep dying. So we see a word that we haven't seen yet, and that word is deceleration. And all deceleration is, it's the same thing as acceleration. It's just we use the word decelerate when the object's slowing down versus speeding up. Okay, so this is still going to be our a variable. Okay, start with our knowns and unknowns. So, look at what we got. First number I encounter is 22 miles per hour. It actually even tells me this time that that is your velocity. So, you didn't know based off of the units. The question itself said, hey, here's your velocity. Write it down for B. Next piece of information, 25 meters also tells you in the problem itself distance. So looking for clues in the problem is really going to help. My unknowns. Calculate time required to stop and deceleration. So time we know is t. Deceleration was that new term. And I just said that deceleration is acceleration but slowing down, so it's still the a variable. Okay, we still use the same equations. It's just a slightly different term because of the fact that the object, in this case moped, is slowing down. So, convert if necessary. Do we need to convert this time? And you won't have to convert for every problem, but I just do usually in class to show you the practice. In this case, we do. We have velocity here in miles per hour, and we want it in meters per second. So we're going to do 22 miles per hour to meters per second. This is where that conversion factor goes directly between miles per hour and meters per second is going to help you. So in this case, we are once again putting the miles per hour on the bottom. Sorry, the lower on the board I get, the more sloppy my handwriting gets. So multiplying 22 times 0.447 gives us around the 11 range, 9.8. Once again, I'm keeping all the digits because I'm not worried about sig figs till the end, but keeping all the digits until then is going to give me a more accurate answer. So that's the units that I want to use, or the number I want to use when I'm plugging B into those equations. All right, so now let's solve for one of the unknowns. Say I wanted to solve for time first. Oh, wait, before I solve, I need to know what equations I'm looking at, don't I? Let's look at what equations. Is it going to be this set or this set? Well, the moped is moving at a velocity of 22 miles per hour. So is the moped at rest initially or in motion initially? In this case, it says it's moving, it's in motion. Okay, so for the first time now, we're looking at the non-zero initial velocity equations. Okay, well that means we're going to have a v, but we're also going to have a vi. So let's look at the v that we wrote down here. 22 miles per hour. Is that its initial velocity or its final? So the moped is moving at a velocity of 22. That's going to be its initial. So I need to update this to v sub I. That's my initial velocity. There, the moped is initially moving at 22. Okay, well then what would my v be? They didn't give me a second number. Let's read. Initially moving at 22, then it decelerates, which we said means slow down, and stops. Okay, so it's stopping. So what is its final velocity if it's stopping? Its final velocity, this v value, is going to be 0. So we have another piece of information that wasn't explicitly given to us, but we can figure it out by rereading. Okay, so that means our v, wherever we see a v, that's going to be 0. vi, we'll plug in there. All right. So if we wanted to solve for time, let's see. Let's look at the first one. We have d, we don't have the average, and we don't have time. So let's keep going. The average, once again, we don't have. How about this one? We got those two, but we don't have a or t. Okay, about this one? A, no. T, no. Down here, notice A and T again. So every single one of those equations, we have at least two unknowns. So how are we going to solve for this? Well, you need to just solve for what you can and go from there. So what I mean by that are, do any of these equations can we solve for? First one, no, because we have two unknowns. We don't know V average, we don't know time. What about the second one? V average, we don't know that, but do we have VI and V? We do, right? VI, V. So we can solve for V average. Well, why would I want to solve for my average velocity if the question isn't asking me to solve for my average velocity? The reason why is because it's the only one I can solve for. And if maybe I can create another known by solving for V average, maybe one of the other equations will work. So if you approach a problem and you can't find how to solve for the unknown it's asking you for, solve for something else you can solve for and go from there. All right, so this is the hardest type of problem you're going to see. So to solve for V average, I have my VI. It is, make sure you're using meters per second version, 9.834. Plus my final velocity, they were stopped, so it's just 0. So it's 1/2 of 9.8. Pretty easy one to solve for at least. 8.4 multiplied by 1/2. 4.917. Units are meters per second because it's still a velocity. So I'm going to add that to my knowns and unknown list over here. All right, now let's look again. Start from the top and work our way down. So now the first equation, we have distance given to us. V average, we just solve for that. So times are only unknown, so we can solve for time now that we've solved for V average. So it helped to solve for some random unknown. So now, using D is equal to V average times time, we're going to solve for time, meaning we have to rearrange the equation. We want T all by its lonesome. So right now, we're multiplying average velocity by time. So to get rid of average velocity, we're going to do the opposite operation, which is divide. We divide both sides by the average velocity, cancels out on one side, and we get a rearranged equation where time is equal to distance divided by average velocity. And then plug in our 25 meters divided by our average velocity, which is 4.917 meters per second. Meters and meters cancel to give us a time in seconds. So 25 divided by 4.917. So it took that vehicle 5.084 seconds to stop. But since it's our final answer, let's make sure we have the correct sig figs. There's always one extra step, isn't there? So we're looking at our original numbers, not the converted ones. So 2 sig figs here, 2 here. So we want 2 in our answer. That's going to round to 5.1 seconds. So now my time has come from an unknown to a known, and it took 5.1 seconds for that moped to stop. But I'm not done. We're going to do acceleration, and then that's probably the last thing we're going to do today. So acceleration now, we have the pick of the litter. It's the only thing we haven't solved for, right? So it's in your best interest, if you can, to pick an equation where the variable you're solving for, in this case A, is all by itself on one side of the equation. So I'm going to use this guy here. That way I don't have to rearrange, and I can just plug in what I have. So A is equal to final minus initial divided by time. So 0 minus 4 point, oops, no, wrong one. That's my average velocity. I want to use my initial. That was a 9. There we go. 9.834. So we're just taking what we have on our list and plugging it in. Time 5.1. Notice, we're going to get a negative number. This is the first time we've seen a negative acceleration. So why do you think we're going to have a negative acceleration? What's different about this problem than the last acceleration problems that we did? We're decelerating. We're slowing down. Every time you slow down, you should be getting a negative acceleration. Every time you're speeding up, you'll see a positive acceleration. So that's a clue there to if you're doing it correctly. Now, I want to make sure I continue doing it correctly and count my sig figs. I want just 2, so my final answer will be negative 1.9. The units are the same as acceleration. So negative because they're slowing down. And they're slowing down at quite a slow rate, actually, too. I think that's the lowest acceleration we calculated out of the 4 different times we calculated it so far today. So what we're going to be doing on Wednesday is we're going to be continuing with these types of problems. I believe I have just one more using these equations. And that's a pretty cool example, a real-world example about fighter jets. And then we'll move on to some different categories, and we'll expand upon these equations, looking at free fall, as well as vector problems. So, all I have today.